Quantum gravity and the search for the graviton.
There are two types of particles, fermions and bosons. Simply put, fermions are the particles that make up matter, and bosons are the particles that keep the matter together. Bosons act as messenger particles between fermions and are supposed to govern the four fundamental forces of nature: gravity, electromagnetism, the weak force, and the strong force. The boson for the electromagnetic force is the photon, the W and Z bosons govern the weak force, and gluons govern the strong force. An example of a boson at work is illustrated in the gluon. Protons are made of three quarks, which are fermions. The job of a gluon is to keep the quarks together, acting as glue. But remember how I said that bosons govern the four fundamental forces of nature? I left out gravity, and that's a problem. We have yet to discover a boson that governs this force. Meet the graviton.
The graviton is a hypothetical particle that would act as a boson for the force of gravity. It is critical that scientists prove its existence. You see, we can explain all four of the fundamental forces in terms of general relativity, which deals with the big picture, but the equations don't work with gravity at a quantum level. Does this mean that there is a gravity particle?
From the time of the Big Bang to 10 to the negative 43rd seconds after is called the Planck era.
During this time, all four of the fundamental forces acted as one. Since they were all a part of a megaforce, they should all be able to be explained at a quantum level. Quantum gravity is an obscure facet of physics, since the particle that would govern it has yet to be discovered, and unfortunately, detecting a graviton is impossible with our current technology.
As gravity is the weakest of the four forces, detecting gravitons would require a sensor so big that it's unfeasible.
However, this doesn't mean that the graviton doesn't exist. It's just a matter of when we detect it and who will discover it.